Welcome to the episode of Handle of a Pan, where I'm going to share with you an application of fin equation and finite volume analysis through visualization, key concept, and math manipulation. So think about when you're cooking in the kitchen and you let the pan sit on a heated stove for a while. Have you thought about the temperature change along the handle? Intuitively, we know that the base of the handle is hot, and the tail of the handle, which is not directly touching the stove, should be cooler, especially when an insulated material is attached to the end of the handle. But how does the temperature change along the handle? Is it a linear temperature decrease or exponential decay? Well, in the next couple minutes, we'll apply finite volume analysis to find this out and also compare the results with the analytical solution. First step, visualization. Let's visualize this problem by modeling it as a fin, which allows us to use the fin equation later. Also, let's assume that the base temperature at point B is 50 degrees Celsius, and the tip of the fin at point A is insulated. The room temperature T infinity is equal to 25 degrees Celsius. Here are some other parameters that we're going to use. The heat transfer coefficient for air, H, is equal to 10 watts per meter squared Kelvin. The thermal conductivity for cast iron is 65 watts per meter Kelvin. The diameter of the fin is 0.02 meter, and the length of the fin is 0.2 meters. We're also going to define P as the perimeter of the handle, which is pi times d. Now we have successfully translated this scenario into engineering language. Yay! Now let's take a closer look at the handle. You see that there are some dots on the handle? That means we're breaking this handle into multiple sections and giving them names. Node 1, 2, 3, 4, and 5. A fancier way of defining this process is called grid generation. The grid size is defined as delta x, which is equal to the length of the object divided by the number of nodes. This delta x basically tells us how fine or how coarse our analysis is. The more points we take, the smaller the grid size we get. It usually gives us a smoother result. As you can see, the distance between the point and the boundary is delta x over 2, and the distance between 2 points is delta x. There are some other definitions we need to get familiar before we move on. Let's use note 3 as an example. The red box represents the control volume around it, and the length of the control volume, as we recall, is also delta x. The temperature at the point of interest is defined as Tp, and the temperature on the east node is Te, and the temperature on the west node is Tw. EF means it's the east face, and WF is the west face. Now that we have visualized our problem, we're going to move on to the fun part, key concepts. The key concept behind the finite volume analysis is to first write out the governing equation. Second, integrate the governing equation over the control volume. Third, relate the integrated equation with different nodes. Fourth, to rearrange the equation to a nice looking form. And then we can repeat 3 and 4 for interior nodes, boundary node 1, and boundary node 5. So let's start with our governing equation. So in this case, we're just going to use our general 1D steady state fin equation. And to integrate, it's also very straightforward. We just add our integration sign and then add dv to each term. And recognize that we can replace dv with area times dx. Then we can perform our integration from the west face to the east face. Notice that the areas can be canceled out, and we're also replacing this hp over ka with m squared to make the equation look cleaner. Now we're left with this integrated governing equation. We can further expand this equation by writing out the dt dx from the east face minus the dt dx at the west face, then minus m squared t minus t infinity times delta x is equal to 0. Now we're done with the integration of the governing equation. We can start relating the governing equation to the nodes. Let's first take a look at all the interior nodes. We're going to pick a random interior node since the equation will work for all the interior nodes. Okay, so let's just pick the one in the middle. The red box represents the control volume. Delta x is the length of the control volume, and we have two faces, east face and west face. Temperature at the point of interest is Tp. Temperature at the east node is Te. Temperature at the west node is Tw. Now we can rewrite equation 2 into this form, where temperature change over distance at the east face is bounded by Tp and Te, so we can use Te minus Tp over delta X. Similarly, temperature over distance at the west face is equal to Tp minus Tw over delta X. The rest of the equation stays the same. Now we're going to rearrange this equation to a very specific nice looking form, like this, with Tp, Tw, Te, and S. And this S means a source term. Essentially, the source term is a collection of terms that do not contain Tp, Tw, or Te. After rearranging, we will get something like this, and m squared T infinity delta X is the source term. And this equation works for interior node 2, 3, and 4. Now we're going to repeat what we just did, relating the integrated equation with different nodes, but for node 1 only. So we're going to draw our control volume right at node 1, where we specify our delta X, east face, west face, Tp. Notice in this case, Te doesn't exist because there's no point to the east side of node 1. Instead, we do know the temperature of point B, which is 50 degrees Celsius. We still have Tw on the west. Now we can write equation 2 in this form, where dt over dx at east face is equal to Tb minus Tp over half of delta X, because this is at the boundary. And dt over dx at west face is the same as before, which is equal to Tp minus Tw over delta X. The rest of the equation stays the same. Now we can rearrange this equation to our favorite nice looking form again. And we can automatically eliminate Te terms because there's no Te in this case. We still have our source term. After rearranging, this is what we got, where Tb is included in the source term. Very similar to how we approached boundary node number 1, now we're going to analyze node number 5. So we're going to draw our control volume right at node 5, where we specify our delta X, east face, west face, Tp, Te. Notice in this case, Tw doesn't exist for the similar reason, because there is no point to the west side of node 5. In addition, we know that at point A, the tip is insulated, which means the temperature change is 0 at west face, which allows us to eliminate the second term in equation number 2. We still have Te on the east side. So now our equation 2 becomes dt over dx at east face, which is equal to Te minus Tp over delta X. And the rest of the equation stays the same. Now you know the drill. We're going to rearrange the equation to the nice looking form again. And we can automatically eliminate Tw terms because we don't have a point that is located at the west side of node 5. We still have a source term, and after rearranging, this is what we have. Last step is math manipulation. Now we have all the nodal equations from previous slides, and the coefficients can be calculated from the known values. It is our job now to replace Tp, Tw, and Te with corresponding temperature node. For example, the first equation at node 1. We're going to replace Tp with T1 and Tw with T2. Same thing for the rest of the equations. Once we have all the equations, we can put them into a matrix form and ask MATLAB to solve it for us. And here is a plot for the temperature distribution. As you can tell, it matches pretty well with the analytical solution. The base temperature starts at 50 degrees Celsius and drops down to about 40 degrees Celsius at the tip, which is just a little bit above body temperature, so it is safe for us to hold it. At the same time, this also concludes our video for today. If there's anything that I mentioned during the video doesn't make sense, please let me know. Thank you again, and I'll see you next time.